Welcome to the presentation Windows 10 TCP/IP RCE from the patch to the screen of death. Today I would like to speak a bit more about the bug which was classified as CVE 2020-16898, also known as a bad neighbor. This is quite an interesting bug, which in the end, during my research, I result in generating proof of concept exploit which had an ability to crash every Windows 10 system mostly updated during this time, which you can see the picture of that problem and the results of the running of the exploit here on this screenshot. At first, I would like to apologize for the quality of this picture because I made it using pretty not professional device, which was my phone. Sometimes I call it potato. However, as you can see, it's kind of show you what is the result of the exploit. Before I move forward, I just wanted to speak a bit about myself. So my name is Adam Zabrocki, among others. Sometimes I use nickname pi3. You can always contact with me using my private email, which you can see on the top right corner of this screen, which is pi3@pi3.com.pl. I also have Twitter account, which you can always find me. And also I have my own personal website, pi3.com.pl, where you can always find some kind of update information how to connect with me. Currently, I'm working in NVIDIA as a principal offensive security software engineer. Before, I used to work in Microsoft in the offensive security research team, also in the European Organization for Nuclear Research, known as CERN, in the HISPASIC system, as mostly known from the Virus Total project, also in the Wrocław Center for Networking and Supercomputing, in Cigital, and few more. On my spare time, I'm one of the main developer of Linux kernel runtime guard, which I fully designed and implemented, and currently is being published under OpenWall umbrella. I also used to be one of the developer for RSE reverse engineering software interface framework, which was one of the first reverse engineering framework with own programming language, which was quite innovative, and it was focusing on the Unix systems, especially in the ELF binaries, where I was responsible, among others, with MIPS architecture. Also, during my spare time, I do a lot of bug hunting, and I found, among others, bugs in the Hyper-V hypervisor, in the virtual GPU implementation for Intel and NVIDIA product, in Linux kernel, in OpenSSH, in the implementation of the stack smashing protector known as Propolis in the GCC, in the Apache server, in XPDF, a few more, and I have CVE numbers for that. And also, I like to study various exploitation techniques, and some of the research which I made was published on the Frag magazine. Okay, let's move forward to the topic of this presentation. So at first, why did I choose to look and analyze this specific type of the bug? Why this bug, not any other bugs? And the answer to this question is quite interesting, because one of the main reasons why I focus on that bug, because this type of the vulnerability we can easily call as the worst possible nightmare. The reason why, because this is a bug in the implementation in the TCP/IP stack, which is very rare, so it doesn't require an authentication. So this is like kind of pre-authentication type of the bug. And because of that, none of the firewalls can ever help, because the bug is during the parsing of the packet which is incoming. So before we can apply any firewall rules, we still need to handle this packet first. So the bug is during the parsing of the code, so the firewalls will never help. It's just in the too early stage where the bug exists. And also, we kind of remotely exploit kernel, which is ring 0 in the x86 architecture, which is the highest privilege mode for the operation system. So because of that, there is no possibility of any kind of sandbox of the vulnerable code, neither any kind of mitigate of that, because we fully remotely exploit kernel exploits, which is kind of disaster. And this type of the bug that you still can find in the TCP/IP in the parsing code is very unusual. So this is kind of a dinosaur among vulnerabilities, which is very rare. And it's not very popular nowadays because this is kind of already old code which have been audited thousands of times. And the expectation is there isn't any kind of surprises like that. However, as you can see, still some of the bugs in the TCP/IP can be found, which is kind of crazy. That's the reason I call it kind of the worst possible nightmare, and it's kind of dinosaur at the same time. But speaking about dinosaurs, as another dinosaurs can be very dangerous, which means that full and weaponized exploit could result in the catastrophic scenario. And this scenario could be fatal in consequences malware, that type of the malware which you cannot defend from, because it's in the pre-authentication phase of the parsing of the package, TCP/IP, which doesn't rely on any user interaction. So you could imagine creating a malware who will just automatically starting to compromise any vulnerable system connected to the internet, which is kind of crazy because everybody thought that this type of the bugs doesn't exist anymore, especially not in that level as a TCP/IP stack parsing bugs. And in the worst, at least we would be able to generate something called Spink of Death 2.0, let's say, because Spink of Death is a type of the attack which existed in the early stages of the Windows, like Windows 95, that you can send just a packet and kill the machine. So this type of the bug, like Bad Neighbor, allows you to exactly generate at least kind of Spink of Death attack to the modern Windows 10 system. So which is pretty bad. So if you take everything together, this is kind of world can burn now. We have pre-authenticated bug in the TCP/IP stack, and you cannot really defend from that, and you can crash any updated Windows 10 systems, which is kind of crazy. Speaking about the timeline about this bug, so on the 13th of October 2020, Microsoft released the fix for the Bad Neighbor bug as a part of just regular Patch Tuesday. And at the same time, there was the first detection signature created exactly on the same day by various companies, including, among others, Sophos, McAfee, and a few others. And the same company who created the detection signature claimed that exploitation of this bug is pretty trivial. And if you know about the implication of the bug and how unusual this type of the bug is and what the crazy implication might happen, it's kind of crazy claiming that this kind of exploitation is trivial because the bug doesn't look trivial at first place and is very critical. However, if you dig in more about their statement, it turns out they just forgot to add one very important piece, that they got proof of concept from Microsoft for free. So essentially, claiming that something is trivial in exploitation, if you get the exploit for free, it doesn't really judge the particular difficulties of how really difficult it is to exploit this bug. And it can be written in the one of these, for example, screenshotted statements that the proof of concept shared with the map partners is both extremely simple and perfectly reliable. So this is kind of unusual that if someone got proof of concept for free saying it's easy to create it. And in the security researcher industry, let's say, security researchers somehow realized that this is not pretty not a good statement, and they're starting to be very criticizing this kind of statements. And so one of the most popular comments on the Twitter was exactly this one. It's easy to say that creating proof of concept is easy when Microsoft hands you one as a part of the map program. So I find it kind of funny, and kind of reply went viral. However, the story about this bug was pretty crazy that everybody's starting to put more and more eyes on this direction. And that's why it was just a matter of the time when the first known proof of concepts will be popping up. So speaking about that, the first known but not public exploit for Bad Neighbor was created around 14th of October. And exactly on the same day, I thought, you have to check it by yourself. Like how difficult it is to create this proof of concept, because the detection signatures company claim it's trivial, but researchers was not able really to create proof of concept. At least none of the public proof of concept existed. And the bug seems like the most critical possible bug ever at that specific time, because it just removed TCP/IP bug in the kernel. So I decided, yeah, you have to check it yourself. There is too many legends around this bug. And I created working POC one day later, on the 15th of October, and here is a screenshot from the WinDBG that one day later I was able to generate a stack smashing on the kernel stack proof of concept for this bug. And day after that, on the 16th of October, I decided that it's a YOLO day. You only live once, so I decided to publish every detail about how to exploit this bug, what's really is behind the scene behind this bug, and kind of remove all of the legends around it. So I decided to publish very detailed write-up about this, including exploit itself with all of the technical details. So where is the bug? So from the Microsoft description, we will not learn much. However, there is still some kind of interesting information. So this is kind of quote from the official statements about the bad neighbor from Microsoft. So what we know that there is this type of the bug is a remote code execution bug, which exists in Windows TCP/IP stack, which incorrectly handles ECMP v6 router advertisement packets. And this ECMP v6 router advertisement statement, like name, is being referenced a few times in this Microsoft description. So what do we really know? Not much. We only know that the bug exists in the ECMP v6 in the RA parsing logic, but nothing more. So this is not a very detailed description and doesn't tell you a lot. However, can we do something with this? In fact, yes. We could try to run IDA and reverse engineering the patch, or we can try to reverse engineering the detection signature. And if doing so, we would be able to find out more information about the bug, because at least we know where to look at. We know we need to look at something around SMPv6 array logic, and maybe we can find more information. So because we have two options, which one to go? I choose to go of analyzing detection logic instead of analyzing the patch. And the reason why, because the patch itself published by Microsoft include more than 40 other patches for other bugs, 40 other bugs. So analyzing this specific bad neighbor among 40 other fixed bugs will be not as easy, not as trivial, because at first you would need to filter them out, which fixes are exactly targeting bad neighbor vulnerability, not other one, and then you can just start doing analyzing the bug bad neighbor itself, which could take you some time. However, in the counterpart, if you just go starting to analyze a virus detection, the detection logic for the bad neighbor, you already have this job done for free, because you just targeting exactly that specific bug, which is much easier because you don't need to filter out any other fixes or any other detection. You just need to focus on the bad neighbor directly. So that's why I decided to go to this direction, because I thought it will be much easier. So speaking about that, I started to look on the internet about any possible description of the bad neighbor from the detection logic perspective. And interesting description I found in the McAfee's website, and I quote it here. So essentially what we know from this statement, that the bug is in the IPv6 array logic, but with the option related to the RDNSS. RDNSS is an option type with the number 25. And if IPv6 array RDNSS says, which is option 25, using the length field, which is a second byte of the option, which is an even number, there is something wrong with the package. And if that happens, and then we flag the packet, otherwise the detection logic jumps to the next 8 bytes of the packet and doing exactly the same verification. And they also wrote a detection signature in the Lua script, which was quite long, but the essence of this detection I screenshot here on the slide, which is these 2 lines of Lua script. Essentially, if the option type is 25 for the ECP v6 array, which will represent RDNSS option packet, and the length is more than 3 in numbers, but at the same time it's also an even number, we flag this package. So it gives us much more information than before. So at first, we know that we need to send RDNSSS packet. So it's much more concrete than just ECMP-v6 array. We know it's array, and we know it must be RDNSS package. Now, additionally, we also learned that the problem is with an even number in the header length field, which gives us a lot of interesting information already because it's related to the length itself. And additionally, we know that RDNSSS parcel will read the last 8 bytes as the next packet's header because it jumps every 8 bytes. So that's kind of a lot of information to start poking around. However, before we go there, I started to read the description about RDNSSS itself, and that we learned that this is one of the ICMP-v6 array headers options, which looks like that. That's the screenshot from the RFC. So we know there's various different fields in this packet. However, we also know that we are interested in that field, which is length. And if you look closer on the description of the length for the RDNSSS in the RFC, we end up in that description. In briefly, what does it say? It says that it's an 8-bit unsigned integer, and this field length include also the length of the type and the left field itself. So if you have length set to any kind of value, it already must be non-zero because it already needs to carry the information about the length of itself plus the length of the type field. Additionally, its being carry information count as a units of 8 octets, and the minimum value of that is 3, which means that if you have RDNSS option send as a part of the array package, that means that we need to send at least one IPv6 packet, and if that happens, that we know that the value must be 3. However, if you want to carry more than one IPv6 packet, we need to add to the length number 2. So if you want to carry 2 IPv6 addresses, then the length will have the value 5. If you want a 3 IPv6 packets, the length will have value 7. So what it tells us at first, that the bug is in the even number, but the description says that there should never be an even number as a length value in the length field. So this is kind of interesting. We know what to look for. And also we know that we always, when we add the new IPv6 address to the RDNSS packets, we also need to increment the length value by 2. The reason is why is by 2, because the units are being counted by 8, and IPv6 has the length, the address of the IPv6 has length of 16 bytes. So that's why if we have a full IPv6 address, we need to have 2 octets. That's why we increase them by 2. And because we start with the non-even number, that's why we will never be able to generate non-even number with the correct RDNSSS packets. And that's like a tons of information for us. So I wanted to starting test and find out what's really going on. But to be able to do that, I need to know what to monitor to be able to run any kind of the tests on the Windows kernel itself. So I started to look about all of the symbols related to the TCP/IP driver in the kernel, which is related to the router advertisement and RDNSSS. And I found these two pretty functions. First of all, it's IPv6p handle router advertisement, and another one IPv6p up update RDNSS. And both of these functions should be related to the RDNSSS, so related to the bug, which we'll try to exploit. So I put the breakpoint on them, and then I started to think how to quickly send an ICMP-v6 array packet with the RDNSSS option. And I wanted to do it fast, because I want to test at first if I'm poking in the correct code. And the best option to do that is to use Scapy. And Scapy could be carried as a self-contained program, or could be also carried as a model for Python. So I wrote this very simple Scapy script who sends the RDNSSS packets. In short, at the top of the script, I declare the destination address and source address. Then I create the RDNSSS option header, which I fill. I set the length to 7 because I want to send 3 IPv6 packets. which will have value a byte. And then I just on the bottom just send that. It's pretty simple and quick. But when I did that, when the packet was sent, I realized that first function, IPv6 handle router advertisement, the breakpoint was hit. However, the second function, which is update RDNSSS function, were not hit, which is kind of weird because the packet is correct, the SCAPI generated correct packet. However, for some reasons, the update RDNSSS was never executed, and I was wondering why, what's going on. So I ran the debugger and I ran the single step, and I in the end end up executing this piece of assembly code, which you can see here on the slide. So what's there? What this specific function, a specific instruction do? And essentially, the register R10, it's pointing to this piece of the memory, which keeps the exactly the package which we sent. So under R10, pointer for R10 points to the memory with the entire package which we sent. And then I realized that I never passed the check, which I mark here on red. So compare of register R8 with the byte 0xFE. I always was failing that specific check. And I was starting to wonder, like, why? Like, what's the story behind it? Why at first in the parsing logic there is some kind of hard-coded value, which is 0xFE, which is related to the package which I sent. So then I started to look what is the first bytes in the packets under R10, because the first instruction, he copies the first byte from the R10 pointer of the R10 to the R8 register, which is later compared to the 0xFE. And then I realized that the first bytes in the packets is in fact keeping the source address of the IPv6, which I sent from my test SCAPI script. And it was correlated to the specific address. And the first byte from this address is FD, which was hard-coded and compared to the 0xFE. So why there is a logic who compares and hard-coded the value of the IPv6 address? And I was very surprised. But then I started to poke around and on the internet, and I end up reading some kind of documentation about IPv6, and I realized that 0xFE as a byte, so any address who starts with the FE byte, it means this is an address of the link local prefix, which means that if I want to pass this check, I need to create as a source address this kind of address which will pass the definition of link local prefix address. In the IPv6 world, it more or less means that you are in the local network. So in IPv4 world, it will be some kind of equivalence of address 192.168, etc., etc. So you're coming the packets from the intranet, not from the internet, essentially. And this is kind of interesting. The reason why, because this is a first limitation of this bug, that if you really want to trigger this bug, we must be able to send the local link address as a source address. Otherwise, we won't be able to trigger this bug. And originally, when Microsoft published the bulletin regarding this bug, they were assigning the CVSSS score 9.8, which is, I think, one of the highest possible. And they were claiming that you are able to exploit this bug from the internet itself. However, when I published my write-up in the blog post, they changed the CVSS to the 8.5, I believe. So they reduced the CVSS score. I don't know if it's related to my publication or they just realized by themselves that you physically cannot exploit this bug if you are not in the local link network. However, that's what I found to be able to exploit this bug, that the source address must be sent from the link local prefix address from the IPv6, which must include the first byte as 0xFE. So I quickly fixed that. And I wanted to trigger the bug. So I sent the packet from the correct local link prefix address. However, to be able to trigger the bug, we need to set the length option in the RDNSSS, which is a second byte, to be an even number. And then when I did that, I ended up in the handler for the RDNSSS, which were ending up executing this specific piece of code. So what do we see from this instruction? So at first, there is a red len field from the packet. which is pointing to the pointer rbx plus 1. And then from the value of the length, there is a subtraction of number 1. And the result of that, or len minus 1, is being divided by 2. So essentially, in the pseudologic, we could somehow generate this kind of pseudocode. Like we read the length, we subtract 1, and then we divide by 2, and this is the result of the parsing of the length field for the RDNSSS. However, as you can see, there is a problem with the even number, because if you have even number and non-even number, there could be two values generating exactly the same value. So for example, if you send the length as a value 8 and we subtract 1 and divide by 2, from the we will have as a result for this operation as 3 if you're speaking about the integers. And the same will have exactly the same output value for the length number 7, because 7 minus 1 divided by 2 and 8 minus 1 divided by 2, both of them generate you the result as 3. And obviously one of them is correct and one of them is not. So that's kind of interesting. And then I starting to trigger this bug again under the sniffer, and I run one of the sniffer and do a screenshot here, and this is what I saw. So essentially when I send this packet with an even number, the sniffer, it was Wireshark at the time, starting to generate kind of interesting output. So I just sent RDNSSS packet, however, as an option to the array. However, in the sniffer, they thought there is some kind of additional header, which I never sent. And it's kind of interesting. And then I realized that the new header, which the stack thinks it's there, the type is unknown with the length kind of big, like 187. However, I mark here on the yellow and red box that the value of the type of the next header and the length of the type of the next header is representing exactly with that bytes which are part of the IPv6 address carried in the RDNSSS option. What physically happened, then the last octet of the last IPv6 carried by the RDNSSS has been treated as the next header when you send the length as an even number. So essentially it means that if you send an even number, the stack of parser of TCP IPv6 is starting to badly calculate where is the next header after RDNSSS. And they're starting to use the IPv6 value address of the IPv6 as a value of the next header. However, they should started doing this after the last IPv6, not as the middle of them. So essentially, what happens that you are able to smuggle one hidden packet there, or one hidden header here. However, what packet could we smuggle as a hidden one to generate something bad? And this is kind of interesting question because we have a lot of options. When we were sent just a random value, we didn't generate any kind of blue screen of that or nothing like that. Just we realized that the packet was correctly parsed, but then in the end they're starting to badly parse IPv6 as a next header. So what could we smuggle in the IPv6 to emulate some kind of another header which will generate something badly on the Windows side? And essentially there is a lot of options, and I listed them here. And in fact, I didn't know, and I don't know which one is supposed to be that one who can generate kind of problematic situation for Windows. So how can we tackle this problem? Which options should we use? We can in fact analyze one by one in the details, but it will take us a lot of time. And I wanted to generate proof of concept as fast as possible. So I started to think that the best option is to brute force them. However, how do you brute force it? Is it even possible to brute force that? And it turns out it's possible because all of the available options must follow exactly the same header layout before carrying the own information. So the beginning of the header must always follow the same bytes layout. So if you want to change the option for the array, we must always generate this kind of layout, and as a type we just create a special number. So the type 22 sorry, 23 will have, this is like a map option. Type 138 will say it's a card request option. So essentially, if you're starting to brute force the first byte, it will be represented as a type of the array option header. So I'm starting to think about doing this. However, before doing that, I'm starting to test one more interesting scenario. Like, what will happen if I starting to smuggle exactly the same buggy header in the header? So if in the RDNSSS option, I will smuggle as a hidden header exactly RDNSSS with exactly the same buggy situation carrying even number as a lamp field. And then I realized that I could trigger exactly the same bug recursively. So essentially, by smuggling various RDNSSS header, I could trigger recursively bug as long as I could. It's kind of funny, but not very practical. But it's possible to smuggle the bug with the buggy header, with the buggy header, with the buggy header, so on. However, by doing this test, I found interesting that when I send these recursive headers in the headers with the buggy headers, that not all of the breakpoints were hit in the same time. So IPv6 phandle router advertisement function was hit as a function only once when I set the breakpoints. However, the update RDNSSS hit as many times as I smuggled the recursively fake headers. And I'm starting to think like this kind of interesting, like how is it even working that router advertisement is only hit once, but update RDNSSS are hit so many times. And to be able to do that, of course, we need to reverse engineer that. So I run IDA, and I'm starting to analyze the handle router advertisement function. And what I found out, it was pretty interesting because I realized that this function has two loops. First, in the first loop, all of the data from all of the headers are validated, of course, except the fake header, which arrives through the bug in the update RDNSS option. However, that's what they do. So at the beginning, they're trying to find out all of the necessary information from all of the headers in the IPv6 and trying to validate them exactly there at that point of time. Then they execute a few other code, and in the end, there is a second loop who have assumption that all of the data is already validated, and they don't do many checks at all. They just skip them because they trust exactly the data because they just validated them in the first loop before. And this is kind of interesting. That gives us pretty interesting primitives in case we would be able to smuggle interesting packet headers. So such logic gives us like a huge potential, but what are the options and what are the headers which could be reacting in the second loop? And then I started to brute force, and I realized that only 4 different type of the options are being handled by the second loop and react. The second loop only reacts on these 4 different types of the options for the array. And it's not many. So I started to analyze all of them each one by one. So the type 25, we already know, this is exactly the bug who calls the bug. And we know that we can recursively call the RDNSSS with the buggy header smuggling another buggy header. However, it doesn't give us much, excluding that we can recursively hit the bug, but it doesn't crash the machine, nothing like that. So I essentially went forward and I put this type as out of scope for now because I couldn't find anything interesting what I could do with. Then I started to analyze the next type, which is 31, DNS search list option. And I realized there's also nothing interesting. When you enable this option, there is only a few bits set in the packets, and that's all. The function returns, and there is also no kind of bugs, nothing is triggered. So yeah, we only left with the 2 types of the headers, and I started to analyze them. And what I realized that both of them, like type 3 prefix information and type 24 route information, they copy data to the stack via function ndisGetDataBuffer. And if you connect this information with the previously described, that the second loop assumes that the data is already validated and they do not check many things, including the header itself, you already know what to do and you know where to focus. You know which types you need to smuggle. So this is what I'm exactly starting to do. I choose just type 24. There is no reason why you shouldn't choose type 3. Both of them will work. I just choose randomly type 24 as a route information. And I put as a fake header exactly type 24. And as a size, I put the maximum possible size which I could set for that header, which was 0xff, because it's 8 bytes long, so the maximum value is 0xff. So I set as a fake header exactly that, and I resend the packet. And what happened? That updated in SSS function breakpoint was never hit, which completely shocked me. It's like, why? Because I was able to smuggle the recursively and the RDNSSS. However, when I changed the fake header to type route information, even the first time updated RDNSSS was never hit. And I was like surprised, like I didn't really change anything. Like, why doesn't it work anymore? So I starting to analyze route advertisement handler again, and I realized that I always fail these checks, which are represented by this free assembly instruction. So essentially what is here, the register RAX or AAX has a number 0x48. However, the pointer, the R15 register has the value 0x40. So if you see the difference between both of these registers are exactly 0x8, which is the value of the truncated packet size when we are using an even number in the RDNSSS for triggering the bug. So essentially, because we send the packet with the even number, we're starting to say how many data we expect to have in the buffers. But essentially, we send slightly more data, and there is exactly 8 bytes long differences. So how to bypass this check and how to be able to still make it work? And in fact, it's not as trivial as it sounds. However, the workaround requires to adding more headers after the magical DNS, some kind of dummy headers. However, it's not as trivial to pass this validation, and it took me some time to create the right package layout, because if you add the extra headers, you also change the size of the packet. And then the header length information, each of the extra header must also match how many packets are being read by NDIS, and you need to align them correctly to exactly not fall into the trap of this free instruction of the check when they verify how many headers length has been declared and how many of them has been read. However, it's possible to be done. It took me some time, and in the end, I was able to pass this check and move forward. And I finally succeeded, but after returning from the RDNSSS function, the handle for the route information, which is the fake header which I hide, was never executed. And I was still like, okay, I think I did everything right, like, so what's going on? So obviously I'm starting to debug, and in the end I end up exactly executing these instructions here listed. So what really happens here? So essentially in the function update RDNSSS, it reads the length from the fake header, which is being read in the register ECX. Then ECX register is being multiplied by 8. This is exactly matching the standard of the RFC, because this the length field is being represented as an octet. So it's the length which has been read has been multiplied by 8. And the result of this multiplication was 0x7f8. So that's the value of the ECX register. And the reason why it happens like that, because I set the value of length of the fake header as 0xff, the maximum possible. So 0xff multiplied by 8 gives us exactly 0x7f8. So this is expected, and this is exactly what we end up having here, and that's good. However, this value is being compared with the value 0xb8, which is coming from the pointer R14 plus offset 18. So, and they're starting to think what it really means, and they realize that this specific pointer and structure under that specific offset, it represents and indicates how much data is transferred from the packets are still left in the buffers, internal buffers. So essentially, they verify how much data the next header needs and how much data have been read by the TCP/IP driver from the packet. So obviously, in this check, the ECX is much higher than the read data. So we expected from the next header to read much more data that has been read from the packet, and that's why we failed this check. So we have in fact two options here to bypass it. We can reduce the size of the fake header, or we can add more dummy headers. and I essentially did two of them. So I reduced the fake header size to not be 0xF but smaller one, and I add a few more dummy headers in the packets, which I increase exactly the value of R14 plus 18 in the structure. And I finally landed in the parser of route information header, yay! So this is exactly what I wanted to do. And now I expect exactly to generate some kind of a bug because they copied the data to the stack. So I expect to have some kind of overflow. And then I ended up in this specific piece of code in assembly. And what does it do? So it briefly reads the length from the fake header, which I set to that kind of value that after multiplying by 8, and this multiplication is done by shifting register bar 3, it generated me the value 0x100. So the value was 0x100 divided by 8. And then next, the length is not validated because the validation were made in the previous loops in these functions. At least this was the assumption that the handler of route and information advertisement will validate all of the headers and all of the sizes in the first loop, and then it doesn't do any verification. And this is exactly what happened here. They just read that value and they pass it to the function and this get data buffer, which has been called here in the mark as a yellow. So essentially, when this function is being executed and this get data buffer, it's supposed to copy the length size data to the very small stack buffer, which is sized of the route information header. So in theory, we're supposed to have a classic buffer overflow on the stack. However, even if we should have a classic buffer overflow on the stack, the overflow didn't happen. And I was again like, why? I did everything correct. Like, why this get data buffer didn't overflow it? And I couldn't find the reason why. And moreover, the getData buffer function should return the address of that buffer where it copies the data. So if we provide a local stack buffer as a buffer where to copy the data, exactly the address of that buffer is supposed to be returned from this function. However, the returned address from this function was completely different from the local buffer on the stack, like completely different volume, nothing related to the stack. And I have no idea what's really going on. So obviously I need to start reverse engineer this function, analyze it, doing single step and as much as possible and analyze which is possible. So I started to doing that. And then I realized that in the function and this get data buffer, I always returns executing this piece of code. What really happens here? I was failing this specific compare, and I would like to jump to the instruction after read, but I was always failing it and I was returning here. And I didn't really know why. So I started to analyze that RCX register has the size of the local buffer on the stack. However, the RAX register has some very large value associated with the packet, which comes from some kind of internal NDIS allocator. So to be able to bypass that, I would need to create a packet very, very small, as small to be able to be small as RCX value. However, if I make it so small, I won't be able to send another extra header. But if I don't send extra header, I won't be able to bypass the previous checks which we have been describing in this presentation. So how is it possible to even pass this check? Because if I put the check so small, I won't be able to even generate the bug. And this is kind of crazy. So I decided, okay, I would probably need to very carefully reverse engineer this function and this get data buffer and analyze what does it really do and why I having this weird situation. But before doing that, I decided to carefully analyze and read the documentation of this function in the MSDN. And by doing that, I ended up finding this pretty interesting piece of information, which I exactly mark here in red. So essentially, this function is supposed to copy the data. However, if the requested data in the buffer is contiguous, the return value is a pointer to the location to some kind of internal NDIS buffers instead of copying any kind of the data. So, this would somehow explain why I was not seeing the pointer for the local stack buffer returning from this function. However, if this function cannot find the contiguous data which has been requested, and the storage parameter is not null, then they will do exactly the copy. Otherwise, instead of copy the data, they will just return the pointer to the internal NDIS buffers where the specific requested data resides. So to be able to do that, I would need to find somehow a way that the data which I sent and later are requested are not contiguous. They are somehow not contiguous. And how to do that? How is it even possible to do that? And in fact, there is a trick to do it. If you use fragmentation, all of our data will never be contiguous because they will be fragmented. So I change the logic of the packets which I send to always fragment any kind of the data. And then what happens? Boom. I finally crashed the Windows. Every puzzles which I put together starting finally to work. So in the end, to be able to generate the crash, I would also need to use fragmentation. And under WinDBG debugger, it looks like that. So as you can see, the stack was smashed with the bytes 0x8a. And because I put pretty long length in the fake header, I smashed the stack in the many bytes on the stack was smashed. So here we go. I was able to finally generate the crash. And machine, of course, bruskin of that. So that's the picture of this of the laptop created by Potato. That's all. Do you have any questions to this presentation? Also, the exploit is available on the bottom of this slide in my website. So you can download the Python script which using Scapy to exactly exploit bad neighbor bug and generate the plus screen of that. And the very detailed write-up which I created, and you can find on my blog, sync on the top left corner in this slide. Thanks.